Number 9. Uh, so, what did you do first? Find the regions where the function has positive slope. Positive slope needs to be interpreted. What does that mean? Derivative is positive. Slope comes from the derivative. So you need to know where the derivative is positive. To find that, first you need the derivative. Then you need to find the zeros of the derivative. Then you need to figure out what about signs around the derivative or around the zeros. Okay, so somebody give me the derivative. Steph, give me your derivative, please. Love it. Okay, now we want to find the zeros. How did you go about finding the zeros? Monica, what did you do for approaching that?
I first factored out an ABS.
Okay.
And then, so I got times the squared plus x cubed.
Like it.
And then I factored out x squared.
Okay. X squared times, and you get 3 plus x, yeah?
Yeah, and then I know ABS can never be negative.
All right. Never zero. Cool.
So then I did x equals 0 and x equals -3.
All right. So your sign test will be divided up among those two zeros, and then surely we could look at the original, but addition subtraction doesn't have hard fast rules on positives or negatives. So you should always try and find the factored form to sign test, because that's what has hard fast rules for positives or negatives. So if you try -5, we said e is positive every time, so I'm just going to put positive for the first term down every time. What about -5 for the square? And the square, isn't it always positive? Okay, so that's cool. But 3 plus x is probably negative over here, then turning positive. Yay? Cool. So this has got a bit of a trick. First, would you agree with my sign test being negative, positive, positive? So is my answer then from -3 to infinity? Yes? How many give me a thumbs up if you say yes? You have no choice but to give me either thumbs up or thumbs down. So there's no sitting there. So thumbs up, yes? Thumbs down. I can't see them. If you put them here like this, you'll way up. Okay, why thumbs down, people? Why not, Jim? Why not the whole set? It looks like positive and positive. Yeah, so is it, let's test here. At -3, what's the derivative? 0. And at 0, what's the derivative? 0. And is it positive at 0? No, it's 0 at 0. So you actually have a little gap in positivity there, and it is from -3 to 0 and 0 to infinity. The derivative is not positive nor negative at 0. It's momentarily 0 there. If the derivative is 0, then what does that mean about the graph of the function? When the derivative is 0, the function's graph has a kind of a flat spot here. If the derivative is 0, the tangent slope is 0. It goes flat there for a second, right? We'll talk more about that tomorrow. Okay, that's a good warm up. You got 2 problems knocked out. Isn't it so much better when you go to sit down at night to do your homework if you have something on the paper? Isn't it just totally discouraging to have a totally blank paper when you're going to do your homework? I hate that. All right, so I always try and get you at least something on the paper. Here we go. Indefinite integrals, yay! The second half of calculus today. You've done differential calculus, or started it, and now we're doing the integral calculus. Are you ready? Great. I'll take one person, that'll do. So, inverses in math, actually, not just calculus, but pretty much all levels of math, we would like, if we have a operation, which is like a verb, it's something you do, to have something that undoes it. So the inverse of addition, for example, is subtraction. The inverse of multiplication is division. The inverse of a power is a root. The inverse of an exponential is a logarithm. Today, the inverse of a derivative is, I'll call it 2 things. An antiderivative, that name makes a heck of a lot of sense, or an integral. All right, let's introduce the old idea. So say you were looking at your homework, but you didn't have your book in front, right? And it says, using good notation, you wrote not just some random garbage like 3x squared, which has no meaning. You used good notation, and you said the derivative of f is 3x squared. Now, without looking at the book, you could probably tell what the original function was. The original function was x cubed, yeah? Are you with me? What about if I told you it wasn't x cubed? What if I told you it was x cubed plus 1? Could it have been x cubed plus 1?
Yeah.
Could it have been x cubed minus 7? Yeah, all right. So if I were to actually say what was the original problem, it would be more like x cubed plus some constant. What should we call that constant? Let's just call it c for some constant. I don't know. There could have been a constant there. Without some more information, I just don't know what it would have been. But it's x cubed, and maybe the constant's just 0. I don't know. But it could have had a constant. You follow? All right, cool. Now let's throw in the notation at this. This question then, the question I said, what was the original problem, means in calculus you would write this something like this. This, that's an integral. It is a Roman S, which stands for sum. And y, we'll talk about that when we get to definite integrals. But for now, the integral is like an elongated s. Okay? dx, that means that really they took a differential with respect to x and they moved the dx over. But our answer is x cubed plus c. So when they give you this kind of notation, you need to decode it and say, well, that means given the derivative, what was the original problem? That's all in there. When you see that integral problem, they're saying the derivative is 3x squared. What was the original problem? So anti-differentiate or undo the derivative. You follow? Why you want to do that? Oh my gosh, I'm so excited for you to see. It will be great. All right, now, as I was talking about with the plus c, all of these could have had been the original here. Do you agree that f of x, the derivative is 3x squared? This f of x, the derivative is 3x squared. This f of x, but sine's derivative is cosine, right? Yeah, but what about sine of 1? What's the derivative of that? Is that a function or a constant? Sine of 1 is a constant, so the derivative of that is still 3x squared, and obviously that's 3x squared. So the point is, all of those equations funnel into the same derivative, 3x squared. So when you integrate, you're actually going backwards, and you don't know if it was 3x cubed, x cubed plus 7, x cubed minus 7. So you don't know if there was a constant there. So you'll always add the plus c, senor, to remind or say there could have been a constant there, you don't know. All right? So with that said, all of these are anti-differential problems, or this is a derivative or a differential. What was the original problem? So, for example, this. What kind of problem gives you a derivative of 7x to the 6th? X to the 7th plus c, because there could have been a constant there. We don't know. Do you understand what I'm asking? Okay, do the other 3, please. Okay, ready? So what's the antiderivative of cosine? Is it sine or negative sine? It's tempting to say negative sine because when you would do derivatives, you think the derivative of cosine is negative sine. But that's not the question. The question is what gives you a derivative of cosine? And that's just normal sine. So then the problem then is, what if I said what's the antiderivative of sine? Well, it's not cosine because the derivative of cosine is supposed to be negative sine. So what must it have been? Negative cosine. There must have been a negative there, knocking out the negative I would expect it. All right. What about the third or fourth one, depending on how you look at it? X plus c, and the antiderivative of 1 over x? Natural log of the absolute value of x. Now, it's important you remember the absolute value because you don't want to leave out the negatives. By putting in the absolute value, that allows you to include the domain in the domain negatives, all right? So make sure that the absolute value is there. That'll be something we constantly fight. All right, now, nailing down the constant of integration. As we said, I could, given a derivative, think the original graph could be lots of things. So, for example, could be f is x squared, could be f is x squared plus 1, could be f is x squared plus 2, could be f is x squared minus 1, could be lots of different things, yeah? All right. Now, if I then told you, okay, yeah, I'm giving you this derivative fact. So here's a family of different graphs. Later on we'll do what's called slope fields, and that'll be a family of, oops, that's not supposed to be intersection. So important. Okay, the point is this. If I told you two things, if I told you, all right, the derivative is 2x, and the original curve passed through the point 1, 1, then doesn't that rule it down or narrow it down to just one possibility? Not all of these go through 1, 1. Only one of them goes through 1, 1. So if you're given the derivative and a point, that will allow you to find the plus c. Now here's the deal. Your goal is to find what the original function was given these two things. First, integrate or anti-differentiate. You say that this way. The antiderivative of 2x, and right now that dx is just going to kind of come along for the ride, and you're not going to be sure why it's there, but please promise me you'll put it there because it's very important to me. There is huge meaning to it, I'll get to. But what is the antiderivative of that? X squared plus c. At that point, we said f must have been x squared plus some constant. Now you sub in the point to find c. All right, so they say when f of 1 is 7 means when x is 1, the function is 7. So what goes where? 7 goes for the function, and for x goes 1. That implies that c must have been 6. And therefore my function must have been x squared plus 6 if it has that derivative, which it checks. The derivative would be 2x, and it passes through 1, 7. That checks. If you put in 1, you get 7. You follow? All right. With that in mind, try these on your own. You are integrating and finding the c. Integrate. Pay attention to notation. Okay, let's see. Maddie, what'd you say for the first one?
I said the natural log of absolute value of x plus
7. Okay. Let's see if I agree with you. Natural log of the absolute value of x plus c is cool. 7, 1. Log of 1 is 0. So that means I agree. C is 7. So natural log of the absolute value of x plus 7 is correct. Are we down? Okay. So the next one, just saying this in a different way. I have the derivative of f, and I want f. So what undoes the derivative? Integral. And whatever I do to one side, you do to the other. So f of x is the antiderivative or the integral of negative sine of x with respect to x, really a good calculus. Is that cosine or negative cosine? Cosine plus c. All right. How do I find c, Mr. Kroger? Yeah, how do I find the c? Now what is it? Just how do I find it? Okay. Beautiful. And what is cosine of pi, Miss Harrington? I agree. And therefore the c is what, Martin? I agree. F of x is cosine of x minus 2. I can verify that by either taking the derivative and make sure it matches, or putting in the point and make sure it matches, but it should match. All right, this one's a little bit of a trickster. This one's hard to integrate the way it is. So what's a good first thing to do there before you integrate that? I'm looking for, yeah, simplify it or rewrite it cleaner. 1/2 x to what power? Oh, you don't know the power rule. Shyster. So it's I kind of got ahead of myself. Do you know what has, we've done that before. What has the derivative of that? Okay, never mind. Sorry, I was going to go power rule, but we don't know the power rule. So there are a lot of rules for integration that we haven't done yet. Sorry, we're just starting. So there's power rule and sum rule and u sub and integration by parts and ultraviolet voodoo and all this stuff we'll talk about. So yeah, ultraviolet voodoo is a real thing. So if I put in f of 25 equals 7, surely you have to be careful to put things in the correct place or you're going to have an error. C here on the last one was 2. And so f of x is root x plus 2. Do you concur? Okay, cool. This guy here. All right. So if I get one that's multiple choicey kind of thing, you're given the, what does this notation mean? The derivative. And how do you get rid of the derivative? Integrate. Technically, you would separate the differentials, but we'll talk about that later. Okay, give that a go and see what multiple choice you would choose. That's an AP question. Notice here you're using y, not f of x. Use the notation of the problem that you're given. Don't make up your own. Okay, Harrison, what's your antiderivative?
Would be f of x equals x to the third plus x to the negative y plus.
That's a bit of a trick. What's the antiderivative of minus 1? It'd be minus x to the first, or just minus x. That would give you a minus 1 as a derivative. And then plus c. Okay, use y notation, not f of x in this case. All right, cool. Now, negative 1 is 1 minus 1 plus c, so feels like c is negative 1, so y is x cubed minus x minus 1. So we choose, which one? B? B. You can see that, gosh, you have to read very carefully here. It would be a shame to do the calculus correctly, but choose incorrectly. Read carefully. All right, cool. Is that all in the notes? Yes. No, easy lesson, yay. Okay, homework on last night's, or questions on last night's homework if you have any. These are the replacements. Unfortunately, I did a key, but then I forgot to post it, so I don't think I had a key online. Speaking of keys online, I guess I should try to figure out a way to, maybe I'll just put a question. I think tomorrow I'm just gonna put a question in the homework that says, go to my website, look at box 7, write in what you see there. Because it's, I don't wanna get hit. Can I see? I don't wanna be too grumpy about this, I mean, but I had answers there, and some of you didn't even give it a good call. And I had, I tried it. Well, okay, you tried it, but come on, is this third grade? I mean, I was a mechanic for 7 years before I was a teacher, okay? And I can't imagine saying to a customer who came in whose clutch didn't work, I worked on it all day, and at the end of the day, the clutch still doesn't work. I said, but I worked on it all day, so that would be $700. I'm not paying you $700. You didn't get the job done. Okay? If you get the job done, I'll give you full pay. If you don't get the job done, I'll give you zero. So don't give me, I tried it. I don't try it. What are you, third grade? Do it well, or don't do it at all. Yes? What is Z?
Yeah.
Z's an integer. What do you mean? Oh, that's all integers. Okay, Z. Okay, are you, so, my point is this, if the answers are there, I'm glad that you took the time to give it a go, okay? Now take a little more time to do it well, those of you who got a 2 or whatnot. You're asking about which one has a Z? I don't know what you're talking about, so talk to me, people. 23? So it feels like Z is just crazy tough. 23, this super R, that's all reals. Super Z, that's integers. All integers. And I imagine, I haven't looked at the problem yet, but I would imagine the answer is all integers. But let's see, shall we? 23. Find all integer values. Okay. So this is actually a great problem because it is an example of what a great mathematician must have. A great mathematician has 2 things going for them. They have studied and have all these processes they've worked hard to learn. But at the same time, they also haven't lost all their common sense. They still see with their eyes open, and they're still a problem solver in the natural born sense, okay? So in terms of this, just forget all the fancy math people, except for what is absolute value. Absolute value is always positive or 0 and up. So tell me, who cares? I don't even care what's inside. Is there anything that's not going to work there? Isn't absolute value always going to be greater than -1? Always? Yeah. And so this is everything. Everything. I could put in W2, fine. Put in -billion, fine. If nothing works or nothing doesn't work, it's all integers. Now, why integers? It's because they said in the question, give me all the integer values that make this true, and so all of them would make it true. As far as the fancy Z, I don't care if you say fancy Z, just say all integers, it's fine. Okay? We don't do a lot of segmentation. All right. So back to this bad boy. Should we talk about an answer or 2 here? 22. 22 is a good one, humdinger. Should we start there? All right. How is the reciprocal idea going? Let's see how you did there. Give me one starting point where the original function blank, the reciprocal blank. Where the original has zeros, the reciprocal has vertical asymptotes. Perfect, okay? So over here, when I take the reciprocal of that behavior, what will my 1 over f graph look like? First of all, will it be above or below the x-axis? Above, because those are positive, the reciprocal will be positive. So I know it's up here. And then shape-wise, gosh, I'm not sure about here. I guess those are getting bigger. So as these get bigger, what does 1 over f get? Smaller. Here, close to the 0, as those get really, really small, the reciprocal gets 1 over small, which is big. And so it should look like this on the outsides. By the same token, down here is negative, yeah? So 1 over small negative is big negative. 1 over small negative is big negative. What's the highest it goes? What y value is the highest it goes to? Negative 1/4. The reciprocal of negative 4 is negative 1/4. Okay? So that's the graph there. The derivative graph. I have a matching activity. Just need to cut the pieces out. We'll do it. It's a good one. All right. So, draw little slopes. Would you draw some little slopes on the original curve? And give me whether they're negative, 0, or positive. Do that real quick on the original graph, because that'll help. Okay, so let's start with the 0 slope. Where is there a 0 slope? At what x is there a 0 slope? 0. Now, if the slope is 0, then the derivative is 0. Okay, cool. Left of 0, I think I get all slopes are negative, yeah?
Yeah.
So where will the derivative graph be? Below. It'll be below over here. All right, so I feel like I know it's supposed to be over here. Now the shape. Numerically, you can always just make up a number. If it helps, it helped me a lot to make up numbers. So say this is negative 1/6, and then this might be negative 1/3, and this might be negative 1, and that might be negative 2, and so on. So it seems like the further and further we get from 0, the more these are getting flat, which means small negative numbers. Close to 0, negative numbers. So what about over here? Close to 0 negative numbers is approaching the axis, yeah, small, flatter negative numbers. Now, these get pretty steep, -2, -3 by my estimate in here. Do they just go like that? Zoom in a little. Do they just keep getting steeper and steeper? Or if you zoom in a little, do they start getting flatter and flatter again? Yeah, they get flatter and flatter. So what do the slopes go back to or start approaching? Yeah, 0. They're gonna get really steep, as steep as possible somewhere in here, but then they'll reach what's called an inflection point and go back to something else. And then what about the right-hand side? All positive and getting pretty steep here, but then less steep. So again, graphically it might look like that. You follow? Okay, that's a good one. 20 or 2, whatever that says. 2 replace. What the heck? So you might have thought, did he really mean x equal 4? Or did he mean x equal -2? And the answer is, I have no idea. I can't remember what I meant. So I guess I'll go with the question that I asked. Don't say, oh, you must have meant. No, it says what it says. -4. At -4, isn't it just this graph? I mean, that's right in the interior of the line, yeah? So I mean, basically this is this line here, and I'm asking what's going on at 4, and that's a big fat continuity. By the definition, does f at 4 exist, or is it defined? Did they tell you, hey, do this when x is 4? Does this tell you do this when x is 4? When x is greater than -2, which would include X equal 4, do you know what to do?
Yes.
Yeah, use this. So is f of 2 defined? Sure is. Okay? F of 4 equals 0. All right? Do they tell you, hey, this is what the function approaches? The limit as x approaches 4. Is it clear what to do and what that limit is? Yeah, it's same function. It's 0. And is what it approaches and what it is the same thing? Yeah. F at 4 equals the limit as x approaches 4. They both equal 0, so we conclude f is continuous. X equals 4. Okie doke. So, I don't know if that was my intention, but that's the question I asked, so there you go. What about this guy? You want to talk about this, number 6, or it was good? You feel confident with 6? Let's just go over the answer. What is the answer to 6? Let me put it up, and if you have questions, we'll go with it. There's 1, 3. Oh, here it is. 6, I have y minus 1. Y minus 1 equals 1 times x minus 0. Or if you like, anything equivalent, y equals x plus 1. Either one is fine. Okay? Did that go well, or do we need to go over that? We'll move on. Good, thank you. Okay, 13. I have 3 and 14/15. Do we say yay on that, or no, go over that? Go over it? Okay, so in 12, the question was tangent line to y equals x to the 2/3 at x equal 8. Right? So this is going to be on a quiz or a test or both soon, so it's hopefully you're getting the tangent line process down. On a tangent line, what do you need to do? First, find a point. Please read carefully. There's 2 types of questions. Find the tangent slope, which is just take the derivative, call it good. And there's give the equation of the tangent line, which is point, slope, It's more, right? So read carefully. This says the tangent line. So the point was when x is 8, what's 8 to the 2/3? Cube root it, then square it, that's 4. All right, so the point is 8/4. The slope, clearly communicating not just what the number is, but what the process is in finding it. How do you find the slope of a tangent line? The derivative, either y prime at 8 or dy dx at 8. I didn't use function notation here. So what's the derivative of x to the 2/3? 2/3 x to the negative 1/3 at 8, or 2 over 3 cube roots of 8. What is 2 over 3 times the cube root of 8? 1/3. So my tangent line is y minus 4 for the point, 1/3 for the slope, x minus 8. That's the ending point to 12, yeah? Now 13 says use your tangent line to estimate 7.8 to the 2/3. So how do I use my tangent line to estimate a value? I plug in. What do I plug in? 7.8 into your tangent. Y is 4 plus 1/3 of 7.8 minus 8. That's a little gross, but 4 plus 1/3 of, isn't that negative 0.2? Or negative 2/10, if you like. We go all fractions. You follow? What's that? We're putting 7.8 into the line. So the idea is the curve looks like this, the line looks like this, and they're at 7.8, they're pretty close. So yeah, the 7.8 is just the x values, all you're plugging in. That's a good question. Now, I didn't even think about it. That would be logical, but yeah, we're just using our line to estimate. So that's where I'm getting my answer of 3 minus 115. 3 and 14. Okay, how about this sand pile one? How'd that go? Good or not so good, or I don't know, let's go over it. Okie dokie. All right, sand is being added to a pile in an inverted cone. So it looks like that. The radius is always equal to the height. I'm just going to record my givens here. When there's so much writing, the radius is the height. At one instant, the radius is 3 meters. If the radius increases by 20 centimeters, obviously that would change the volume. Use differentials to estimate the corresponding change in volume. All right, so this is what I would like to see in your work. True change in volume can be approximated by dV. Then, when you do differentials, dV is found by taking V prime at the initial radius times dr. All right. Now, hopefully you got that much. Now, the problem, though, is the volume equation for a cone, isn't it 1/3 pi r squared h? And there is a way to take a derivative of two variables there, r and h, but we haven't learned it yet. So that stinks. Can we replace h with something r-ish so we can make it all r-ish? Yeah, if they're equal, then isn't that volume is pi over 3 r cubed for this problem, yeah? Not for every cone problem is the radius equal to height. It just has to do with the viscosity of the material, yeah? All right, so then dV is, what's the derivative of V? If V is pi over 3 r cubed, then V prime is pi over 3 times the derivative of r cubed is 3r squared, and that has to be at r initial. What was the initial r? 3, okay? Times dr. How much the radius will change by? How much will the radius change by? 20 centimeters, which in meters is 0.02. We want all the units to be the same, certainly. Okay? So we get pi times r squared is 3 squared, so that's 9, times 0.02. 9 times 2 is 18. Move the decimal twice. I feel like that's 0.18 pi. What are the units? Meters cubed. So by the radius changing about 20 centimeters, the sand, 20 centimeters, that's about this, the sand pile volume would change roughly half a cubic meter. Okay? Are those other replacements? I think those are other replacements. Other questions? Oh, no. At the back, there's 2 replacements. On the back, number 1, what'd you get? 1 is A, I agree, and B, never mind, 2. I get negative 81, yeah? Okay, so I'll be happy to go over those, but those are the answers for those. Any questions you'd like to talk about? 19, okay. Others? Shout them out if you like. Today's a short lesson, so it's one of the few times where you can really knock this out of the park and get stuff perfected if you are motivated enough. 31. 19. All right, let me know if you have anything else. I'm going to tackle 19 right here. Oh yeah, that's a bit of a humdinger. I think I had something like 2 natural log of x minus log of x plus a half equals log of 2, yay? Okay. I want x by itself, so I want to get rid of the logs. Is it allowed? Is it a math thing to say e here, e everywhere? That is not allowed, okay? It's a lot like if you said, here, this is true. I think you'll agree that that's true, yeah? 2 plus 3 equals 5. If I said, hey, square here, square there, square everywhere, is that true anymore? 4 plus 9 equals 25? Not true. Okay, so the point is, when you exponentiate or logarithm, it has to be a whole side at a time, not here, here, and here. So you must combine logs first. So if you combine logs using log rules, this one log rule is that a coefficient can be brought up front. Another log rule is when you subtract two logs, it's the same as the single log of the difference, or the quotient rather. Now it's single log equal to single log. Now I can exponentiate a whole side at a time and do well. When I do that, I get something like x squared over x plus a half equals 2. Wait. If I multiply this over, I get x squared equals 2x plus 1. If I move everything to one side, I get x squared minus 2x minus 1 equals 0. And it feels like that factors, but does it? No. So that doesn't factor, which means we could either complete the square or quadratic formula. What do you want to do? Complete the square? Great. X squared minus 2x. It's actually less work, believe it or not. What goes there? Plus 1 and plus 1. So x minus 1 squared equals 2. X minus 1 equals plus or minus root 2. X equals 1 plus or plus root 2 or 1 minus root 2. Now let's check domain. 1 plus root 2. Would that be positive and therefore allowed in the original problem? Cool. What about 1 minus root 2, given that root 2 is about 1.4? Well, that would be negative. And negative in that space right there, no good. So this answer gets dumped, domain style. Only this is a satisfactory. Cool. Any other questions on set 31? Or on tonight's homework, if you like. If you see one on tonight's homework that you have been doing badly, or you'd like to walk through together. Yes?
15.
On tonight?
No, I'm not.
Last night? 15? Sure. 15. Yeah, that was a little crazy. Alright, so this actually is good preparation for, oh shoot. So the idea is you want to use similar triangles to get this R. You can't find the volume of the water until you know the radius of the water. So if you use similar triangles between the cup and the water, that should allow you to find the radius. I think it's 1.5 by scale factor. That should get you. Does that make sense?
Yeah, thank you.
You're welcome. Okay, have a great day. Okay, oops, stop the recording.